Welcome back to another wonderful episode of Dave Does Math from Home. Today we're talking about section 8.2, integration by parts. In this section, we're essentially going to talk about how to do the product rule backwards. So, an age ago, in section 5.5, we talked about how to do the chain rule backwards, and we called that integration by substitution. So the chain rule had, composite functions. We had an inside and an outside, and we took the derivatives of both and combined them. When we did it backwards, we needed to account for the inside and the outside, and that other piece that was the derivative of the inside that came from the chain rule, it all got wrapped up when we did it backwards. So here we're talking about the product rule. So the biggest difference between this and 5.5 is that there's not going to be an inside function. It's just going to be two functions multiplied together, no inside or outside. And we're going to have to use this technique instead of substitution. I mention that because one of the biggest challenges I think that students face in Calc 2 exams is knowing which integration technique to use, because that's not information that I'm going to give you on the exam. Like when you're doing the 5.5 homework, that's the section for integration by substitution, and you should recognize that all those problems are substitution problems. And when you're doing this homework, it's the section for integration by parts, and you should recognize that that's the technique you use for all of these. But on a test or a quiz, I'm not going to tell you what technique you should be using. I'm just going to say integrate this thing. And you have to recognize whether it's an integration by parts problem, or an integration by substitution problem, or a trig substitution problem. There's these different techniques that you need to be able to utilize and recognize. And the distinction between substitution and parts is a tricky one to recognize because they both involve two functions being multiplied together. This one because it's the product rule backwards. Substitution because there's an outside, or there's an other function that multiplies the outside-inside situation. So both of these things involve function multiplication, but in very different ways. And the key thing you can use to recognize them is that these, by parts, have no inside-outside business going on, and the substitution problems always do have an inside-outside business. So that is the general preamble about all of this. To get us started on how to reverse the product rule, I want to remind us of what the product rule looks like. So if I start with the function f of x equals x times the sine of x, the derivative of that should be, this is two functions multiplied together, so it will be the first times the derivative of the second plus the second times the derivative of the first is just 1, so this is the derivative of x sine x. We get x cosine x plus sine x. So, if we know that this derivative works like this, then I think me asking you for the integral of x cosine x plus sine x dx, I'm hoping that this is an extremely easy problem for you to do right now. Because we literally just found that this is the derivative of something. So the integral of this thing is just the original function we started with, plus c, of course. So if we start with x sine x and take a derivative, we get x cosine x plus sine x. That's fine. If we start with x cosine x plus sine x and take an integral, we're back to the original function x sine x plus c. So we can go back and forth like that, that's fine. We also know, if I just ask you for the integral of sine x dx, you know that one. That's easy enough to do. That's just negative cosine x plus c. So now the question becomes, what happens if I just ask you for the derivative of x cosine x? I'm sorry, not the derivative, the antiderivative. The antiderivative of x cosine x. This is sort of a problem for us because it's got that product rule thing going on. This is the product of two functions being multiplied together. And we know that multiplication isn't safe, so we can't just say that this is x squared over 2 times the sine of x. That's not how this whole integration derivative thing works, not at all. But we can use addition and subtraction tricks here. Addition and subtraction is safe. And because addition and subtraction get embedded into the product rule like this, we can use these sort of sneaky tricks to figure out what just this one piece of this should be. So the integral of x cosine x dx, I'm going to say, that's the same thing as the integral of x cosine x plus sine x dx minus the integral of sine x dx. So this integral of sine x dx and this integral of sine x dx, addition and subtraction are safe, so these things can cancel each other, and then you just have the integral of x cosine x, which is what we want. That's what we're interested in. All I really am interested in is this integral of x cosine x. And I'm going to do it by taking this thing, which I know the antiderivative of, because of the product rule. It's x sine x. I know that one. I know the integral of this because it's very easy. Integral of sine x is negative cosine x. So I can just subtract these things. And then I'll have my answer. This thing is x sine x. I'm going to worry about the plus c's later. The c's are arbitrary constants, so when you take an arbitrary constant and you subtract a different arbitrary constant, you get an arbitrary constant. So I'm just going to have one c at the very end. In this situation, it's fine. Much later in the semester, we'll get to situations where you do have to be very careful about what your arbitrary constant is. This is not that situation, so we can be kind of easygoing with our plus c and just put 1 at the end, because addition and subtraction are safe. So I know that this integral is x sine x because of the product rule, and I know that this integral is negative cosine x. I know that there should be a c attached to the end of all this. So yeah, the integral of x cosine x dx is x sine x plus cosine x plus c. This is not exactly integration by parts. Integration by parts is much more of a generative technique. This is sort of like just a demonstration that happened to work because we took the derivative of this and knew that its antiderivative would be back to the same thing. But the principles of integration by parts are sort of embedded in this, in that if you take an entire product rule result and then subtract out half of it, you get the other half, and that other half is the important piece that we're sort of looking for in this process. So let me talk about that in very vague theoretical terms before we get deep into this actual process here. In vague theoretical terms, let's assume we have two functions, u and v. And these two functions, u and v, are being multiplied together. And I want the derivative of that. The derivative of this is going to be the first times the derivative of the second plus the second times the derivative of the first. And in fact, I don't want to use the derivative arrow for this one. I want this to be an equation so that I can mess with it. So I'm going to use the derivative operator. Derivative of u times v is u v prime plus v u prime. This is the product rule in its most vague and generic form. First derivative of the second, second derivative of the first. Just the product rule. I'm not sure why they chose to use u's and v's for this, because those two letters look weirdly similar. But here we are. U's and v's are standard. So, the cool thing about this is I can subtract a part of this from both sides. And then I get the derivative of u times v minus, I'm going to switch from primes to d's here. So v times du, I just like d's better. V times du is what I just subtract. I can switch it here as well. V times du is how I want to write this. And this is going to be u times dv. Okay. So, the derivative of u times v minus v du should just be this piece, u dot dv. That's, again, this is a lot of like symbols, kind of a mess, but all I've done is I took the derivative of u times v using the product rule, I subtracted half of that from both sides. I did this because I want to now take the integral of this whole thing. If I integrate everything, the result is the integral of u dv is, that's this, the integral of u dv equals, this whole thing has been an equation, so I'm allowed to do this, subtracting things from both sides, integrating both sides. I can do whatever I want to an equation, as long as I do the same thing to both sides. And I have done. So this side of the equation, the integral of u dv, equals, this means the integral of the derivative of u times v. So that's just u times v minus, addition and subtraction is safe, so I can just put the integral here as well. This is minus the integral of v du. This is the formula. This is the technique. This is the piece that you badly need to write in your notebook in a place that's really easy to find, and you can reference it very easily, because this is the key to integration by parts. It's this. And it comes from stuff that we already know. It comes from the product rule, subtracting something from both sides, and then integrating the whole thing. That's it. So that's what I mean when I say that this is the product rule backwards. It really does come very directly, very immediately from the product rule. I want to, right now this is probably still very theoretical, very like not grounded, which is why I left this here so that I could draw the connections between these things. And I want to do that now. Let's do that in red. I have this fancy red marker. So the point of this formula is that it is a transformation. You start with the product of two things in an integral, and you transform that into a product that does not involve an integral minus the integral of a different thing. So this, like, I'm often a very strong proponent of using equal signs to be like bidirectional. Like you can go both ways through an equal sign. This is very much directional. We start with something like this and we want to transform it into something like this. We're going in this direction through this equality, which is fine. So here, this is my u, this is my dv. X is u, cosine is dv. So based on this, I'm going to transform it into this piece right here. This is the integral of the derivative of u times v. Remember that I've erased it by now, but we took the derivative of x times sine x, and we got this thing through the product rule. And so if we integrate that whole thing, we're just back to x sine x, which is my u times my v. Which checks out. X is still u. If cosine is the derivative of v, that means that sine is v. And this piece right here, this is the integral of the derivative of u times v, which means it's just u times v, which it is. It's the u times v, it's right here. This is the integral of v du. So, again, if u is x, then du is dx. So that's this. This dx is just my du. And if dv is cosine x, that means that v is sine x. So this is the integral of v du, which for us worked out very nicely, because we know what the integral of sine x dx is. It's just cosine. So when you subtract these two things, you have the integral of just this. The integral of u times dv is u times v minus the integral of v du. And that's how we're going to use this. So we're at about 18 minutes at this point, and I am through with my highfalutin theoretical explanations of what's going on. Tune in to part 2 for a barrage of examples of how we're going to use this with a lot less theoretical rambling going on in the background.